So let's do an example. I have one example and one your turn. A 10-kilogram box slides down a frictionless incline which has an angle of 30 degrees to the horizontal. What's the net work done on the box as it slides 2.5 meters down the incline? Let's draw a picture to visualize this. So we have a box sliding down. It's going to slide down 2.5 meters. And there's an angle to this incline here, which is theta. So theta equals 30 degrees. And it's frictionless, no friction here. The mass is 10 kilograms here. So what's the net work done on the box? So net work means the sum of all of the work. So what we have to actually do for this problem is draw a free body diagram and figure out which forces are doing work. So if we just look at this box here, then there's a normal force perpendicular to the surface. So this chapter is a good review of free body diagrams here. The weight going straight down, so Fg going straight down, normal force perpendicular to the surface. There's no friction. If there had been friction, it would be to the left here. There's no friction. There's no force pulling it down. It doesn't say something's pushing it. It's only sliding down the incline because of the weight. So is the normal force doing any work on the box? Well, the box is moving downward. The displacement is down the incline here. That normal force is perpendicular. We learned in that sign of the work video that a perpendicular force does no work. And that's why we spent a whole video on this, just so you can see how important it is. So Wn, which I'll say the work done by the normal force, is 0 because n is perpendicular. So I'll say because, I'll just abbreviate BC, because n is perpendicular to delta x. Now Fg, we know that a component of this force will do work. So we have done work with the inclines. It probably wasn't your favorite topic, but we're looking at it again here. So that weight going straight down here has a component that is perpendicular to the incline, which I'll call Fgy, and it has a component that is parallel to the incline, which I'll call Fgx. So we know that a force in the same direction as a displacement, Fgx here, is in the same direction as delta x, that it will do some work on that box. Fgy will not do any work because it's perpendicular. So we just have to find the work done by Fgx. So we can write the work done by Fgy is also 0. So the work done by Fgx is going to be the force times the displacement. So we learned when we're dealing with inclines that if we're given that theta here, it's the same theta as that little theta up there, that Fgx component is opposite, uses sine. So the work done by Fgx is equal to Fg, which I'll just write down as mg, the weight, times sine of theta times delta x. So now we're finally ready to write down all of our numbers. We have 10 kilograms for the mass, 9.8 for g, sine of 30. If you remember, sine of 30 is always 1/2. It makes your calculations easier. And then we have the displacement, the distance is 2.5 meters. So we multiply all of these numbers together, and I got 122.5, so I'll round to 123 joules. So there's one more part to this example. So part B says if the box starts from rest, then what's the speed after it has slid those 2.5 meters? So you may think, oh no, now we have to go back and deal with forces and kinematic equations, but this is where the work kinetic energy theorem comes into play. We learned that the net work, which we can call W net, or sometimes you'll see it written as network like this with the summation symbol, is equal to the change in kinetic energy, 1/2 mv squared minus 1/2 mv initial squared. So if the box starts from rest, that means that v initial is 0. that means it doesn't have any kinetic energy to begin with. So that means that the net work done on the box is equal to its final kinetic energy. So we can use this relation to solve for VF. Get it by itself, multiply that net work by 2 to get rid of the 1/2, and then divide by m. Right? Divide by m and multiply by 2. That will get rid of the 1/2 and get rid of the m. So divide by m here. And then that will give us VF squared, and then we have to take the square root of both sides in order to get VF by itself. So this will give us VF by itself. So the numbers that we're going to plug in here to get VF, the net work is what we just found in the previous slide, which was 123 joules, but use the unrounded value of 122.5 in your calculations, times 2 divided by 10, and I got 4.9 meters per second. So that was an example of using the work kinetic energy theorem. Once you know your net work, then it's pretty straightforward to find out final speed. Just multiply by 2, divide by m, if that initial kinetic energy canceled out, as it did because we were starting from rest. I got one more your turn in this video. So it's the last one here. You slam on your brakes in a panic and skid a certain distance down a straight level road. If you had been traveling twice as fast, what distance would the car have skidded under the same conditions? So you might, look at this and be like, I have no idea. But it's in the work kinetic energy video, so maybe it has something to do with that. And in general, if you are given information about there's some kind of force and some kind of speed is changing, then it's probably a good candidate for the work energy theorem. And there is some force here because you have your braking force and it's causing you to slow down. So that's a good candidate. So let's write down that the net work equals the change in kinetic energy. And if you are skidding, that means you're going to come to a rest. So when you do the 1/2 mv final squared minus 1/2 mv initial squared, and for the work, let's just assume that the only work done here is the work done by that braking force, so the force of the brakes times that distance. So we can cancel out the final kinetic energy because we're not going to have any because we come to a stop. So what this question is asking is, well, if this V initial here had been twice as much, what would happen to that distance that it takes for the car to stop? So you might think, oh well, if you double V, then you double D. But look, that V initial is squared. So it turns out if you double V initial, then if you have 2 V initial, you're doubling it. That whole thing is squared. So you end up having 1/2 m times 4 V initial squared, which you can write, you can take that 4 to the front here, 4 times 1/2 mv initial squared. So you're going to actually have 4 times the distance because you doubled something that was squared. So that's all for this video. So just to recap, when you can calculate the work done on an object, you can relate that to how much the kinetic energy of that object changes using the work kinetic energy theorem.